In this video, we begin our discussion of Chapter 6, and in particular, we're going to focus on Section 6.1, hence the title of this chapter as Chapter 6.1. Our goal is to learn about discrete probability distributions. So, let's get right to it. To begin with, our first goal will be to distinguish between discrete and continuous random variables. In Chapter 1, we learned about the difference between discrete variables and continuous variables. Just to bring it back to mind, an example of a discrete variable would be the count of the number of coffee cups you drink weekly or even daily. Then, if I were to spin that variable around to become a continuous variable, I would say that it would be the number of ounces of coffee drunk daily. What is the fundamental difference between these two variables? One, when you are counting the number of cups of coffee, you can only get integer values. That would be an example of a discrete variable. Otherwise, when you're measuring the number of ounces of coffee that you're drinking based on their weights, then you're talking about a continuous variable. Here's the punchline. If you have to count to get the values, then more likely than not, you're dealing with a discrete random variable. Otherwise, if you have to measure to get its possible values, then you're dealing with a continuous random variable. Our focus at the end of this module will be, or the end of this chapter, chapter 6 precisely, will be to be able to answer questions as this. And what does this question say? A student takes a 10-question true or false quiz. Because the student has such a busy schedule, he or she could not study and guesses randomly at each answer. What is the probability of the student passing the test with at least a 70%? Here are a couple of things to note. What variable is of interest in this case? Take note, it will be the number of questions that the student guesses correctly. So, we observe that that is so because if the student is going to pass the test with at least a 70%, then we're looking at least a 7 out of 10. So the variable of interest here, we're going to call that x. That will be the number of questions or answers guessed correctly. Having defined what the variable of interest here is, x, that is the number of answers guessed correctly, the next step we would like to note would be the possible values of x. That is, what are the possible numbers of answers that can be guessed correctly by the student? In the worst case scenario, it could be 0 out of all 10 questions. It could be 1, 2, 3, and as you might guess, in the best case scenario, it could be 10. Notice something. The possible values of x here are all integer values, and any of these values are all possibilities in this scenario for this student. Take note, each value, let's say the student actually takes this exam or this quiz. The reality is if the student gets a 7 out of 10, we are saying that we arrived at that 7 because you counted the number of answers guessed correctly. And that will make x a discrete random variable. Let's take another example. Small companies might be interested in the number of long-distance phone calls their employees make during the peak time of the day. Suppose the average is 20 calls. What is the probability that the employees make more than 20 long-distance calls during peak time? What is our variable of interest here? This time, arbitrarily, I'm going to let the variable of interest be y. And as you might reckon, it will be the number of long-distance phone calls that employees in this small company make during the peak time of the day. This is equal to our y. That is the definition of the random variable of interest here. Having defined what our y is, the next item of interest would be the possible values of y. The worst case scenario, it could be 0 calls during the peak time of the day. It could be 1, it could be 2, it could be 3, and it could continue. Notice in this case that these could continue forever, infinitely. There is no upper cap in this case. This is also actually accounting for a count variable. That is, y here can only assume integer values that are arrived at after a counting operation. So y again is a discrete random variable. Now we've been throwing the word random variable around for a little bit. That brings us to the question, what is a random variable? You see, a random variable is a numerical measure of the outcome of a probability experiment. So if you toss a die, what are the possible outcomes? 1, 2, 3, 4, 5, 6. Take note, each of those numbers represents the count of the number of circles on each of the faces of the die. That is a random variable. It can vary from one performance of that experiment to another. And every time we observe the outcome, it's a number. That is what a random variable is. Whenever you use numbers to represent the possible outcomes of any statistical experiment, that would be a random variable. So, because of the randomness, it means its value is determined by chance. Even if the outcomes of a statistical experiment are described in words, we can still assign numerical values to each outcome based on some defined rule. And in such a case, the variable of interest still becomes a random variable. In general, you see, just like you see me use here, X and Y, I used uppercase letters to represent the first random variable and the second random variable, which I'm circling on the screen. We use uppercase letters such as X and Y and so on to denote the definition of the random variable. Whereas lowercase letters such as X and Y can denote the possible values of the random variable. So take note, this is the punchline. The random variable is written in words, whereas the lowercase of that letter that represents the random variable represents the possible value of that random variable. Now that we have defined some examples of a random variable, we proceed more specifically to zoom in on how to identify a discrete random variable. Let's take an example. In an opaque bag, there are only 6 blue, 3 red, 2 yellow, and 1 green marble for a total of 12 marbles in a bag. So the graphic below, this graphic right here, depicts the distribution of colors across all marbles in the opaque bag. So you have the 6 blue, the 3 red, the 2 yellow, and the 1 green marble. What's our interest here? In question A, suppose the opaque bag only contains marbles. What is the probability of pulling a hat out of the bag? One emphasis to note in reading question A here is that the bag only contains marbles. So that tells us pulling a hat out of the bag, unless you're a magician, will be out of the picture. So in this case, the probability of pulling a hat is the same as the probability of an impossible event. This might remind you of what we learned in the previous chapter. We stand a 0 out of 12 chance of pulling out a hat out of a bag that only contains marbles. So you have 0 here. Question B. What are the chances or probability of pulling any marble out of the bag? Emphasis on the word any. without considering its color. What is the sample space of this experiment? To begin with, the sample space of this experiment would be either pulling a blue marble, a red marble, a yellow marble, or even a green marble. Then, looking at the probability of pulling just about any marble without any consideration for the color, it means I stand a 12 out of 12 chance, which is equal to 1. That is, since the bag only contains marbles, pulling any marble stands what? A certain chance of what occurring. So, in this case, we have looked at the worst case scenario, probability of pulling a hat, an impossible event, and up to probability of pulling any marble. Since the bag only contains marbles, definitely this is going to be 1. It's a certain event that we can pull a marble out of the bag. Recall that this illustrates that every probability value should lie between it will never occur and it will surely occur. Now we proceed to build up on this to talk about a probability distribution. In this case, when we talked about the probability of any marble being 12 out of 12, we might probe even further and say, how are the chances in question C of pulling any marble split or distributed among the different colors in the bag? In other words, what is the probability of pulling a blue marble, or maybe a red marble, or a yellow marble, or even a green marble at that? Let's see. Probability of pulling a blue, taking it back to the visual here, this means I stand a 6 out of 12 chance, same as 1 over 2. For now, I'm just going to leave it as 6 over 12. What about the probability of pulling a red marble? This would be, I stand 1, 2, 3. 3 chances out of 12 of selecting a red marble. And by the same line of reasoning, probability of yellow will be 2 out of 12, and probability of green will be just 1 chance out of 12. So it stands to reason that I can see how my 12 out of 12 has been split among the different possible outcomes in the sample space, or distributed. Well, in order to summarize this finding, question D requires that we summarize the distribution of the total probability that we got in part B, that is the 12 out of 12, among what? The different colors. I can specify this as possible color outcomes. So, in this table, I have documented the different possible color outcomes. It could be blue, red, yellow, or green. And then for blue, we had 6 out of 12. Red was 3 out of 12. For yellow, it was 2 out of 12. And for green, it was 1 out of 12. This table is an example of what is known as a discrete probability model. How so? First, it documents the possible outcomes of drawing a marble of any color from the bag and the associated probabilities for each possible outcome. Then, another reason is very, very important. Reason 1, each probability is a number between 0 and 1. 0 and 1 inclusive. Reason 2 is that the sum of all the probabilities, that is combined, is equal to 12 out of 12, which is 1. Remember, that was what we got in part B. So any table where you have all the possible outcomes of a statistical experiment all the probabilities associated or the respective probabilities for each of the possible outcomes. And we also find that these two properties are satisfied is called a discrete probability model or a discrete probability distribution. Now that we have established what a discrete probability model or a discrete probability distribution is, let's proceed further. Suppose we decide to code the colors of the marbles in the sample space of part D as follows. We let a random variable x be defined based on the following rules. We're going to let x be equal to 1. So I'm going to do that. I'm going to let x be 1 depending on what color is chosen. So we're going to let x be equal to 1 if the color is blue. And we're going to let x be equal to 2 if the color is red. And x equal to 3 if the color is yellow. And x is equal to 4 if the color is green. Take note that when x is equal to 1, the color is blue. And if the probability that the color is blue is 6 out of 12, it is the same as the probability that x is equal to 1. Because when color is blue, x is equal to 1. So the likelihood that the color will be blue is the same likelihood that x would be 1. So we can document the probabilities here too. The probabilities associated with each possible outcome: 6 out of 12, 3 out of 12, 2 out of 12, and 1 out of 12 that we got earlier. Recall? All right. Now I have converted each of the possible outcomes to numbers. This x is an example of a random variable. It is a random variable because the value it assumes depends on a random event or a random trial of an experiment of picking a marble by chance from an opaque bag. Now, in question F, based on the table you obtained above, is x a constant? Like, is it just a single number? Or is it a varying quantity, a variable? I would argue that x is a variable because it varies from 1 to 2 to 3 to 4, depending on what color of marble is possibly selected. Question G, what type of variable is x? Why is it this type of variable? X is a discrete, can be said to be a discrete random variable. And the reason is that it can only assume a finite number of possible integer values. With the reasons established that x is a discrete random variable, because it can only assume any of a set of finite integer values, we establish what typifies a random variable as a discrete random variable. 1, its possible set of values could be finite or countably infinite, and it can only assume integer or count values. And that brings us to the difference between discrete and continuous random variables. You see, a discrete random variable has either a finite, that is, a definite count of possible values, or a countable number of integer counting values. We saw an example of a countable number when we looked at the first illustration here, when we're talking about the number of long-distance phone calls small companies' employees make during the peak time of the day. You observe that it can take 0, 1, 2, 3, but there is no stop to this possible set of values. But particularly, each of the values are all arrived at after a counting operation has been carried out. So, going back, we'll see that anytime you have a random variable that can take an integer or countably infinite number of non-decimal or natural counting numbers, this will be called a discrete random variable. This visual here tells you that it can only take count values, not numbers in between. It does not take numbers like 0.5, 1.2. No, it does not. In contrast, a continuous random variable has infinitely many values, which may be contained in an interval. So it can go from 0 to 4. So unlike integer values that can take only specific values 0, 1, 2, 3, 4, a continuous random variable has values contained in a continuum. And usually, its values are obtained as a result of a counting operation. An example would be the weights, the heights, or the speed of a car. All of these quantities are measured quantities and are examples of continuous random variables. With that said, let us see an example where we will learn to determine whether a random variable is discrete or continuous. You want to recall that for discrete, the punchline is its values come from a counting operation, and it can only take integer or count values. Integer or count values. Whereas for a continuous random variable, its values come from a measuring operation. Let me write this well, a measuring operation, and it can take real, integer, or decimal values. So to begin with, question A. The number of light bulbs that burn out in the next week in a room with 17 bulbs. I will need to count this. So that makes this a discrete random variable. I'll put D for discrete and then C for continuous. So C for continuous. Then for question B, the time required to download the file from the internet. Well, I would definitely be measuring that using an instrument called time or clock. So this is a continuous random variable. C, the number of customers arriving at a bank between noon and 1 p.m. What do you think? Would you be counting or measuring? I will be counting. So that gives me a basis to claim that this variable is discrete. D, the amount of rain in Seattle during April. That would be measured. That makes it continuous. What about E? The number of hits to a website in a day. That can be counted. So would that be continuous or discrete? I would argue that this would be discrete. Then question F. The amount of snow in Toronto during the winter. That would need to be measured, and that makes it a continuous random variable. Then for question G, the number of defects in a roll of carpet. We can count that. That would make it discrete. The weight of a T-bone steak. That can be measured, so that makes it continuous. I, the number of free throw attempts before the first shot is made. That can be counted. That makes it a discrete random variable. And then finally, in a random sample of 20 people, the number with type A blood, that can be counted, and that makes it discrete.